Strategyproof Learning advice. Go ahead. Yep.
Okay. Good afternoon, everyone. My name is Cherlin, and today I will present to you our work on Strategyproof Learning with advice. And this is joint work with my advisor, Balkanski. So first of all, what is Strategyproof Learning? The idea is that we may want to run a learning task on data when our data comes from strategic agents. So people who have a vested interest in the outcome of our algorithm and therefore may choose to misrepresent their information, thereby impacting the outcome of the algorithm. So the classic example in the literature, which is work by Cherlin and Gallian, studies how Zara makes decisions about how they send inventory to different stores. So what they do is they ask each store manager to report how much demand they have for each item type. And then based on this, they will run an algorithm on that. And this is going to output the inventory shipment decisions. And what Carol will show is that the store managers are actually misreporting the demand for their items in order to increase their own personal revenue. And so this motivates the idea of applying mechanism design to learning tasks. And mechanism design just studies algorithms when we consider how strategic agents are going to interact with the algorithm. So to give you an idea of the model, we're going to have some number of agents, and each agent is going to have a set of input points. You can think of these as the item types, so the X values, and a set of labelings. And you can think of these as the demand for each item. And so each agent is going to report, potentially erroneously, their labels. And these, along with the true input points, you can think of these as public information, go into the mechanism. And this mechanism is going to output a function that maps the X values to the Y values. And then based on this function, the mechanism designer is going to incur some notion of risk. But also, each agent is going to incur a notion of risk based on this function. And that's where that incentive to misreport and try to manipulate the mechanism comes from. And so this model introduced by Deco et al. More formally is for each agent I, we have a set of public points, the XIs, IJs, and a set of private labelings for each input point, the YIJs. And so these two together form the data for that agent. And then when agents report their labelings, this forms their reported data. And so now a mechanism has to select a function from a set of function class, given this reported data set. Remember, this is potentially erroneous. And so the goal of each agent is to minimize their personal risk, which is just the average loss of their points with respect to the function. And similarly, the goal of the mechanism designer is to minimize the global risk, so just the average loss over the whole data set. And at the same time, we want to do this in a way that's strategy-proof, meaning no agent I can decrease their personal risk by misreporting their information. And we should note that this has to hold no matter what the other agents are doing. So this is a pretty strong condition. And so now our mechanism takes in the label data, and then it outputs a function. And the main obstacle in this setting is that in order for a mechanism to be strategy-proof, it often has to incur more risk than when we don't have this constraint. And so strategy-proof learning has there's a lot of work in this area. And one thing that's important to note is that the results are often very pessimistic. And oftentimes there's even very strong impossibility results, even on the most simplest of tasks, because of this strategy-proof condition. And so to this, we apply the with advice framework. So what does this mean? This is a recent line of work that seeks to improve the performance of algorithms and their mechanisms by incorporating black box advice about each individual instance. And very importantly, we don't make any assumptions on the quality or the accuracy of this advice. And so this gives rise to two metrics. The first is consistency, so the approximation when the advice is correct. And the second is robustness, so the approximation no matter how bad your advice is. And so you can see there's this trade-off here on trying to depend on good advice while not leveraging it too much when it's bad. And so this framework was first applied to online algorithms, where the advice is with respect to future values. But more recently, it has also been applied to mechanism design, where the advice gives you information about the private values of the agents. And so this is a area that started in 2022, but you can see it's been rapidly growing. And so what we do is we initiate the study of strategy-proof learning with advice. And so if we return to our mechanism model, we're just going to augment the mechanism with advice on what we think the optimal function should be. And so what we are trying to answer is, can advice be used to achieve better approximation in strategy-proof regression and classification? So I will spend most of this talk on our regression results, specifically fitting a constant function, which I know you think should be a very easy task. However, what we will see is that by requiring strategy proofness, even fitting a constant function becomes a pretty difficult task. So as I said before, our goal is we are trying to minimize the risk of our mechanism. In this case, it's going to be the average absolute loss. And of course, we have to pick a constant function. And so we know that the optimal function is just going to output the median of the labelings. But this isn't strategy proof. To show you that, so what I'm going to do is I'm going to show you an instance with 3 agents. So this is just the first agent, this green agent. And I have plotted his labelings. And where the green agent is his optimal output. So he wants the output to be as close as possible to this. And so now if we introduce the other 2 agents, we can see that this star is the median, or the optimal for the mechanism designer. However, if we allow the green agent to misreport, even just 1 point, then now the median has shifted. And so you can see it has moved to the green agent's optimal point, thereby benefiting him at a cost to the mechanism designer. And so this is why just selecting the median is not strategy proof. So in the without advice setting, Deckel et al. Present a deterministic strategy-proof mechanism that achieves a 3 approximation. And they also show that this is tight. In other words, even for fitting a constant function, you can't do better than a 3 approximation. So our first main result is that we provide a deterministic strategy-proof mechanism that for a parameter gamma between 0 and 2 is 1 plus gamma consistent. So recall that this is the approximation when the advice is correct. And 1 plus 4 over gamma robust. And this is the approximation no matter how bad the advice is. And then we also show that this is tight under some mild constraints. And so just to give you an idea of what this result means, if we set gamma to 2, we're going to recover the 3 approximation from previous work. But if gamma is really small, we're going to get near optimal consistency while still maintaining constant robustness. And just really quickly, our other results on regression are that we show our mechanism is group strategy proof. So this is just a stronger notion of strategy proofness. We present the approximation as a function of the advice error. And we also get the same guarantees for the task of learning a homogeneous linear function. Okay. So let me present the mechanism. So once we set our parameter gamma, what we do is we first look at each agent's labelings. And then we are going to find the median point of that and call that BI. And now we're going to make a new data set by taking the points for a single agent, take their points and move it to his median, BI, and then add some copies of the advised constant. And the number of these extra points is just going to be proportional to gamma. And then we're just going to take this new data set and return the median. So what this looks like on our little toy example is that take all the agents' points, map them to the median. And then in this case, let's assume that the advice is correct. So if we add some copies of it, then the median is exactly the optimal, which is great. But you can imagine that the advice may be completely off. Of course, this is going to impact the performance of the mechanism, but of course, our robustness bound shows that this isn't too bad. And so really quickly, the way that we prove that this consistency robustness trade-off is tight is on a high level, we're going to require the mechanism to be strategy proof and 1 plus gamma consistent. And when we do this, this is going to restrict the behavior of the mechanism on a series of instances. So our first instance is that we have a bunch of red agents. They all have labeling of 0. And a bunch of blue agents. They all have labeling 0 and 1 with a slight preference towards 1. And the number of each agent is going to depend on gamma. And so if we have advice, in this case it's correct, of 0, we show that in order for this to be 1 plus gamma consistent, we have to return something that's less than 1. Now, because we have this restriction on this instance, when we allow the blue agents to move their 1 labels to 1 plus delta, in order to maintain strategy proofness, we still have that condition of returning something less than 1. And then we can keep doing this. We keep shifting those points of the blue agents until really, really large D. And even still, we have to return something that's less than 1. And now if we shift everything, so the red agents now have almost half 0 and half D, except a slight preference towards 0. So 0 is still their preferred outcome. And the blue agents have all their label as D. On this instance, the optimal should be large D. But if we have erroneous advice at 0, then in order for this to be strategy proof, we still have to output something less than 1. And you can imagine this is really bad. In fact, it is 1 plus 4 over gamma minus epsilon bad, which is exactly how we get our trade-off tightness proof. Okay. Really quickly, I'm just going to speed through our results on classification. So in the without advice setting, Meyer et al. Show that no deterministic mechanism can do better than linear approximation in the number of agents. And they also provide a random mechanism that is 3 approximate, and they show that this is tight. What we show is that essentially advice isn't helpful at getting better consistency. Precisely, any deterministic mechanism that gets consistency better than linear has unbounded robustness. And any random mechanism that has consistency better than 3 has at least linear robustness. And so you can see by applying advice, we aren't able to get better consistency without the robustness blowing up. However, this isn't the case if we restrict to 2 labelings, we can do better. And so really quickly, this is just a chart of our results. And so in conclusion, we initiate the study of strategy-proof learning with advice. We show that in general, advice is useful for regression tasks, but not so much in classification. I didn't cover this here, but we show that all of our positive results generalize to the setting where agents have data instead of just being set points, are drawn from a distribution using some pack learning techniques. And in terms of open questions in this area, of course, we could consider random mechanisms for our regression settings. We can study the classification when data is realizable. And we can also consider incorporating advice when agents are able to misreport their actual input values instead of their labelings. So thank you for your time, and I'm happy to take questions.
Questions is either.
Hey, thank you very much. So, what changes if we move to a setting where we can consider randomized algorithms for this?
Specifically regression?
Yeah, first setting yeah.
Yeah, so we don't know because the previous work doesn't consider randomized. Our suspicion is that it shouldn't get too much better, but that is a area that's worth looking to. Now, as for classification, you can see it's a lot better.
And is there a specific motivation, I guess, from the real world to study deterministic, or is it just that it's a nice, clean problem to think about?
I think in terms of mechanism design, for this setting specifically, the deterministic part is a really nice thing to consider. Perhaps not this application in particular, but there are other mechanism design problems where if you are trying to explain what you're doing to people, they don't like randomization. That is very oftentimes the argument for deterministic in mechanism design.
Thank you.
Thank you. Yeah, quickly, I was actually interested in the last item that you mentioned, which is the case where the agents would be misreporting their values, which I think is actually something that has been studied quite a bit in online learning or regret minimization, basically strategic regret. Which brings me to two questions. What do you think would happen actually if the agents are misreporting? And what happens if you cast all of this in an online setting?
Yeah, so you're right that a lot of the previous work are in those two settings. A lot of them also, when allowing agents to misreport their inputs, they might put a cost on the agent's risk when they can misreport, because I think allowing them to misreport their input I think it makes the control that the agents have over the mechanism a lot larger. There's a lot more ways they can influence what happens. Mm-hmm. So I've seen imposing a cost on misreports somehow, maybe in terms of the level of deviation. And then I have also seen it in settings where, like you said, regret minimization in the online setting. I haven't seen with advice used for regret minimization, but I think that is an interesting area for sure.
Sounds good.
Thank you, speaker again.